Hello everyone, my name is Jaziel, and the title of our paper is An Exploratory Study on Extract Method Floss-Refactoring. Refactoring is an activity in software development that seeks to improve software design while its external behavior remains unchanged. In other words, a refactoring is a code edit that aims at improving quality-related aspects of a source code, such as readability and maintainability, but without changing the external behavior of the software. However, even though software behavior should remain unchanged after a refactoring edit, several studies evidence that refactoring often leads to error proneness, and this problem is even worse when developers integrate refactoring and non-refactoring edits. That is, when apply a refactoring with behavior-changing edit, such as adding a new function or fixing a bug. This activity of adding refactoring with other edits is known as floss-refactoring. Here we have an example of a floss-refactoring edit collected from the Broadleaf Commerce Project repository. On the left, we have the original code, and on the right, we have the floss-refactored version. In this example, an extract method was applied to extract lines 8 and 9 to the persist part method. However, many other edits were also applied. First, the method signature was changed. The parameter library, which was an unspecified set, now has a specific type, integer. Second, an if statement was modified to check the hash code of an object instead of the actual object. Change in conditional expression like this can impact the software behavior if not carefully analyzed, since a code might be executed or might be prevented from being executed when it was supposed to. Here, the hash code is stored in the library instead of the object itself. This can impact the software behavior if all references to the library were not carefully analyzed. Here, a new condition was added, and as I said before, it can prevent a code snippet from being executed. At this point, a cache verification was deleted. Another if statement was updated with newly added condition. And here we have the most dangerous so far. A code snippet was placed to run in a separate thread, which might open the software to a set of unforeseen faults related to concurrent programming. After pointing out many risks in floss refactoring, Kim et al. Stated the need for new software engineering tool to support floss refactoring. And to that, it is necessary to understand how extra edits are applied during floss refactoring. However, little has been done on characterizing extra edits on floss refactoring. Therefore, our main goal in this paper was to investigate the relationship between one of the most common refactorings, the extract method, and extra edits. More specifically, what extra edits are more likely to appear in the presence of an extract method, how the number of extra edits is affected by the presence of the extract method, and how these extra edits are applied. To run this investigation, we propose an automatic approach for mining and extracting floss refactoring data from real software repositories. Our approach is composed by three steps: detecting refactoring edits, checking behavior changes, and detecting behavior change edits. On the detecting refactoring edit step, we mine Git repositories using a refactoring detection tool, refdiff, to find all refactoring edits applied throughout the project's versioning history. We chose this tool because it can find refactoring through static analysis, and it was optimized to run directly on Git repositories. As a result of this step, we have a list of refactoring and the commits they were applied. Then, on the checking behavior change step, for each commit containing refactoring edits, we check if they presented behavior changes. For that, we use the safe refactor tool, which checks for safe refactoring edits. It analyzes two versions of a program, and by generating and running a set of unit tests, it indicates whether the program behavior remained unchanged. Then, in the context of our study, only the commits that presented behavior change were selected to the next step. Finally, On the Detecting Behavior Change Edit step, we list the extra edits applied in commits with both refactoring and behavior changes. For that, we use the Change Disler tool, which is a tool that compares two versions of an abstract syntax tree and classifies the source code edits performed between them. However, Change Disler cannot distinguish whether an edit is part of our refactoring or if it is an extra. For instance, if a new method is introduced in the code, Change Disler cannot tell if the method is a extracted method or if it is a new functionality. Therefore, we created a filter to automatically separate edits that are part of refactoring operation from the edits that are not. The filter we create takes into account the refactoring set detected by refdiff to analyze each edit found by Change Disler. But for the filter to work properly, we needed to modify Change Disler output in order to get essential information about the edits returned. As a result, the filter returns a list of only extra edits. With our approach, we ran an empirical investigation with the goal of understanding how developers combine Extract Method Refactoring with extra edits in practice. For guiding our investigation, we set three research questions. The first, which extra edits are more likely to appear alongside Extract Method Refactorings? Second, how the number of extra edits changes based on the frequency of Extract Method Refactoring? And the third, how Extract Method Floss-Refactoring are performed. In this study, we analyzed 16 open source projects from GitHub with a combined amount of more than 100,000 lines of code. From the 76 144 commits we analyzed in this project, 539 commits contain refactoring and extra edits. Here we have the frequency of all refactoring found by refdiff. As we can see, extract method and move method were by far the most common refactoring. And even though extract method ranked at second in frequency, it ranked first when we consider the number of commits it appeared. Here, we have the frequency of the extra edits under analysis, with statement set as the more frequent edit, and additional object state as the less frequent among these edits. For the analysis method, we decided to use regression models because it can evidence how two variables, the dependent and independent ones, relate to each other. Moreover, regression models has already been used by several other studies to describe the relationship between two or more variables. According to Hilby, Poisson and negative binomial are the most common distribution for counting data. But, due to the great variance of the extra edit in the data we collected, we use the negative binomial distribution, since Poisson requires the data to have equal mean and variance. Additionally, hurdle models are typically used to model the zero count when it is too high. Hurdle models are basically divided into two parts: a regular logistic expression, which focuses on the presence or absence of the edit, and the count model, which focuses on its frequency. This is the general structure of the models we built, where extra edits predicts the frequency of a given extra edit, refactoring is the number of extract methods in a given commit, and beta 0 and beta 1 are the found statistical coefficients. For this analysis, we are focusing on beta 1, since it represents the impact that a refactoring has on the extra edit. Moreover, we built independent model for each type of extra edit. To better understand our results, we use odds ratio representation, which is given by e to the beta 1, where beta 1 is the coefficient of the independent variable in each model. The odds ratio indicates the increase or the decrease in the likelihood of the dependent variable, in this case the extra edit, for a unit increase in the independent variable, in this case the extract method. For instance, if a logged model has an odds ratio of 1.2, it indicates a 20% increase in the odds of an extra edit to appear, while the odds ratio of 0.8 indicates 20% decrease of this event happens. For the count model, an odds ratio of 1.2 indicates 20% increase in the number of occurrences of an extra edit, while an odds ratio of 0.8 indicates 20% decrease in the number of times the event happens. To answer our first research question, we focused on the logged model. In this case, all 8 models we built were statistically significant. That is, the odds of any of the extra edits under analysis appear is impacted by the presence of an extract method. Coincidentally, all edits had increased odds, with statement delete having the highest increase and statement parent change the lowest. This means, for instance, that in real world there are 26% more chances of an extra new method to appear alongside an extract method. There are also 40% more chances of a new statement to be introduced, 45% of a statement to be removed, 39% of a statement to be updated, and so on. For the second research question, we focused on the count model, and from the 8 models we built, 6 were statistically significant. Coincidentally, for this analysis, like in the previous one, all significant edits also had increased odds. However, neither the remove functionality nor the additional object state were statistically significant. From the significant models, statement parent change had the highest increase and statement update had the lowest. This means, for instance, it is expected an increase of 16% in the amount of statement parent change edits, 10% in the amount of statement insert edits, 11% in statement delete, 8% in statement update, and so on. To exemplify our results, let's take a second look at our motivating example. In this code, we have 2 examples of statements being introduced simultaneously with the refactoring, a new if statement and a new method invocation. Here, a method invocation statement was deleted. Here, a method invocation statement was updated. The developer also applied a conditional expression change in 2 different if statements. All this edit has the potential to impact the system behavior, as I explained before. Therefore, our models in fact reflect how developers perform floss refactoring in practice. Continuing, in order to get a more thorough analysis, we also investigated how extract method floss refactoring are performed. For that, we analyzed edits inside refactored edits. Take a look at this code. Both methods has extra edits. However, only the second one was refactoring. Thus, we consider only these as inside refactored entity. In our data, about 13% of the extra edits were performed inside refactored entities. And this was the frequency of each entity type for each extra edit. To answer this research question, we built regression models relating the extract method with each entity type for each extra edit, resulting in 20 models. From these, 14 models achieved statistical significance. All 5 for statement set, 4 for statement delete and statement update, and only 1 for statement parent change. Let's take another look at our motivating example. This statement set is an example of statement set method invocation. While here we have another statement set, but now it is an if statement. A method invocation that was deleted, a method invocation that was updated, and here 2 examples of if statements that were updated. In conclusion, we presented a novel approach for floss refactoring data extraction. Moreover, we showed that some extra edits, such as additional functionality or statement set, are more likely to appear in the presence of an extract method, and some type of statement, like method invocation or if statement, are more likely to be modified. As future work, we intend to extend our analysis with a larger variety of systems as well as analyze other refactoring and extra edit types. We also intend to investigate the impact that each extra edit fault may generate during software evolution, and to work on a mutation tool for automatically introduce faults based on the refactoring found in a given system. Thank you.